So, right, as I said, we have elimination going in one direction, addition going in the other direction, dehydration versus hydration. We've gone over the mechanism for the dehydration, right? This is just an E1 elimination, right? And the addition, the hydration, is going to be the exact opposite, right? So all the intermediates that are formed in one direction are going to be the same intermediates that form in the other direction. So we just need to rationalize how we get from here, right, back to the alcohol. So who can describe their first step?
Water, the oxygen would bind to the alkene and carbon, like the center carbon.
Okay.
That double bond would be the positive charge.
Okay, yeah, so you're seeing that we need an oxygen-carbon bond, right? But unfortunately, right now, this carbon is not electrophilic, right? And so this theme, when we're looking at addition reactions, or alkene addition reactions, we have to understand these pi electrons as being nucleophilic or negative. Right, so that's how that functional group is going to react. So if we think about the last step of the elimination, right, if we're using water as a base in this elimination, right, the last step to get to the alkene is that water is going to pluck a proton. Sigma electrons will fall down to form the pi bond, pi electrons. And we make our alkene plus H3O plus. Right, so to go in the opposite direction, the way that we would illustrate this, we'll have our acid, right? We have sulfuric acid and water. The alkene electrons will be basic. They're going to reach out and grab a proton, and then the oxygen-hydrogen bond will be broken, right? And that's going to form water. We have a lot of it in the addition reaction with carbocation. Okay, so this arrow that we're drawing here is somewhat ambiguous, right? Because all we're doing is we're showing that the pi electrons are reacting, but the arrow doesn't indicate which carbon those pi electrons are staying with versus which carbon those pi electrons are breaking away from, right? So the way that I have it drawn, if we lead to this intermediate, right, those pi electrons are leaving the tertiary carbon, staying with the primary carbon, and then making a new bond to hydrogen. So you can imagine kind of them flipping up like that, right? In which case we'd form a cation at the center and a hydrogen there. Right? This same arrow can be used to also illustrate the formation of the primary cation. Right? And so that's what I mean by that mechanism arrow being somewhat ambiguous, right? Because it doesn't give us the information about which carbon is forming the cationic center, becomes the cationic center. Right? But why would this make sense and not that?
It's more stable.
It's more stable, right? That's I mean, if we think about stability of carbocations, right? Tertiary cation is going to be way more stable than the primary cations. And so even though the arrows don't show which carbon forms the cationic center, becomes the cationic center, right? Based upon what we know about cation stability, this is where that step would lead. Okay. Make sense? Okay. All right, what's the next step?
Water attacks the carbocation.
So this is where we make our carbon-oxygen bond. Right? So now that we've formed the electrophilic center, we can use the nucleophile, right, add to that electrophilic center. Right, and then we form the protonated alcohol, and and then to get to the alcohol product, what do we need to do?
Use water to depermeate water.
So we have a bunch of water in this reaction, so we can use it as a base, pluck the proton off, and that's going to get us to the alcohol. Questions about this? Okay, really important that this hydration, just like the dehydration, involves the formation of a carbocation. And as such, rearrangements are going to be possible, and we have to talk about them. Okay, so using the mechanism that we just showed up here for the hydration, see if you can draw the major and minor product that would form whenever you take this alkene and treat it with HBr, right? This reaction obviously is not a hydration, so there's no water. Very notable that there's no water in this reaction, right? We will use a solvent, but it's not going to participate mechanistically in the reaction, right? And so this is going to be called, this type of reaction is going to be called a hydrohalogenation. Right, specifically a hydrobromination. Right, realize that this is a strong acid, and we're using those pi electrons from the alkene as basic electrons, nucleophilic electrons. Think you need more time? go over this. Okay, so first step, you can describe the first step.
You're gonna break the double bond and draw the arrow to the hydrogen and break the bond between the hydrogen and bromine.
Right, so that double bond, those pi electrons are reaching out, grabbing a proton, and then we're releasing a bromide anion. Right, and this is going to result in the formation of two different cations, carbocations. Right, we have the tertiary cation, and then we're also going to be able to form a secondary cation. Right, and these two cations are what leads to the two different products. Okay. So for the tertiary, obviously we're just taking the bromide, adding to the tertiary center. And for the secondary, we're taking that bromide and adding it to the secondary center. All right, which of these is the major product?
Is it the tertiary one?
Good, yeah, so this is the major. The secondary will be minor. And we refer to these, or you'll hear these referred to sometimes as the Markovnikov product. The other one is the anti-Markovnikov product. Right, and so there's a Russian chemist, last name Markovnikov, who studied these addition reactions, these hydrohalogenation reactions, and found that the major products in his alkene addition reactions were the more substituted alkyl halides, right? The minor products were the less substituted alkyl halides. And so we refer to the more substituted addition products, the Markovnikov product, less substituted as the anti-Markovnikov product. Right? Why is this the major product? Why do we form more of this in the reaction? Thinking about it from an energy perspective, an energy diagram perspective.
The carbocation is, well, the tertiary carbocation would be more likely to exist because it's more stable. So
Good, so the tertiary carbocation is more stable. Why do we form more of it, or why is that the major product in the reaction though?
I was thinking about it. There's more of those carbocations, there's more tertiary to carbocation.
Okay, what about the pathway leading to that tertiary? What can you say about the pathway? Yeah,
The activation energy to reach the intermediate would be lower.
good. Right, so it's not just a thermodynamic argument, but we also have a kinetic argument, right? The tertiary cation is lower in energy, right? And so the pathway leading to that tertiary ion is also going to be lower energy activation, right? And so this will be a faster rate. More of it will be generated, or it will be generated faster, and so it's going to dominate the reaction. Right? So we'll proceed through a slower rate, and there will be less of it in the reaction. Questions about that? Okay, I think this is a good stopping point. If you have a chance after the exam Thursday, try to start reading through chapter 15. Take a look at some of the addition reactions that we're going to learn. And try to go through this chapter pretty fast because it's basically just a series of addition reactions. We're going to look at the reactions and the mechanisms and the products. See you, most of you, tonight.